Thanks, Matt. Hi, everyone. Today I'm going to talk about DeepSpeed. It's a library for efficient deep learning scalability. This is work from a lot of contributors. DeepSpeed, when we created it, the goal was to create this open source library for distributed training, because we recognized early on that this would be important. And the goals that we had then was basically to make distributed training easy, because model scientists are the ones who primarily be doing this. We wanted to make it efficient, so as you scale, it's very expensive from a compute and resource perspective, so we wanted to ensure that the workloads were running as efficiently as possible, so you're getting the biggest bang for your investments. I wanted to make it effective as well, so this is more from a data efficiency perspective. And on those points, so like from efficiency perspective, we've seen that DeepSpeed can run with high performance, whether you're running a single GPU or you're running over 100,000 GPUs. We think the adoption really has been driven by the fact that it's actually easy to sort of get running out of the box once you install it. And democratization was also something that we also kind of highly value, which is basically sometimes the cost of state-of-the-art models can be quite prohibitive because of the hardware investment. So we also work on techniques that help to lower the budget requirements for you to be able to use state-of-the-art AI. So it's on GitHub, and that's just a screenshot of our page. So why did we create DeepSpeed? It was based on the observation that scalability is what drives deep learning, right? The industry is driven by scalability. And here on this plot, I'm highlighting two dimensions, and there are others, but I think so the two primary dimensions of scalability. On the y-axis, you have the model size, which is basically in the millions of parameters going up. And on the x-axis, you have the tokens that you use to train your model, right? So in the billions of tokens. And so if you can sort of point your attention to breakdown there on the lower lens, we could think of that as being the ground day zero for the current wave of deep learning, right? The model then was just about 300 million parameters trained on I think some hundreds of billions of tokens at that time. And if you can then point you to the top right-hand corner, which is sort of where we are today, Llama 4, which was talked about earlier, there we're basically at hundreds of billions of parameters of model train, and then trillions of tokens, tens of trillions of tokens training. So that's basically how things have scaled. And so because of all of the scalability challenges, basically they create a lot of systems to put a lot of pressure on the system resources. So on the compute side, on the memory side, on the communication side, on I/O side, on data, and so in other words, what I'm showing here is that the advancements we've had in deep learning have really been held up by innovations along these four pillars that I'm showing. And in particular, DeepSpeed, we've been working on all of these areas and creating solutions along the way. And looking at the models up there, I'm sure you recognize most, if not all of them. The ones I've highlighted are the models that have been trained using DeepSpeed. And so even though the project started out at Microsoft, some of these models, which are external models, are not necessarily Microsoft only. And this is because DeepSpeed has been open source from day zero, right? So we've had this opportunity to collaborate with the community, and together we've been able to build the solutions, and they've been able to build the models. So I'll talk about the real key challenge that we tackled in the early days, and sort of what kind of, I think, put DeepSpeed on the map is like the GPU memory wall problem. And this is shown here, where here on the y-axis I'm showing, scaling in terms of the model size. This plot is very popular, it's from UC Berkeley, and x-axis is showing time, and it's basically comparing the size of the model to what the accelerated HBM memory that's available at that time. And you can see there's that point where it just sort of crosses over, and then your model cannot fit on a single GPU. And that was roughly around the 2020-ish Megatron LM time. And because the models were growing at about 100x every year, the HBM is kind of like, just growing 2x every 2 years. And even if we project forward till today, and the projections show up there, with like the B300, we're still just going to end up with about 280 gigabytes of HBM. So it's still, not sufficiently large enough. And so this is the first problem that we tackled. And we did that using two key solutions that I would just sort of summarize here. The first one is zero. And zero is this optimization that we designed for the data parallel training, data parallel training paradigm, where traditionally data parallelism has the model states replicated on all the ranks. And with zero, we came up with this idea of, instead of replicating, why don't we partition and you duplicate across. And so then that helps us to reduce the memory footprint per GPU and allows us to fit in much larger models. Then the other direction we went in was like, well, your servers come with other heterogeneous memory like your DRAM and your local NVMe. We could also leverage that memory as well. And those are typically like orders of magnitude bigger than your HBM. And so the zero comes in like 3 different flavors, for the various kind of partitioning schemes that are in there. And that helps to fit extremely large models onto your GPU. 3D parallelism, kind of like a subset of what previous speaker spoke about, where you're able to use auto parallelism strategies to sort of partition your model state. So tensor parallel, pipeline parallel, and then zero parallel. But the main takeaway here is that plot over there, where it's sort of still building on that GPU memory wall plot that I showed earlier, but now it's showing what DeepSpeed, when you bring in DeepSpeed's systems capabilities, like if you see that there, and you see that DeepSpeed actually is scaling even faster than the models are growing. So, roughly just looking at the impact, we provided system capability to train trillion parameter models as far back as 2021. So this is well ahead of the model scientists. The techniques which I've listed here inspired other frameworks like FSDP and Colossal AI, Megatron LM, we've all sort of adopted the zero optimizations. So I want to spend the rest of the time to just talk about some of the new things we've been looking at in DeepSpeed, and there are basically 4 things that I'll highlight today. So the first one is universal checkpoint. And the motivation for this is that now, distributed training, states are distributed, whether you're doing pipeline parallel, tensor parallel, or zero. And the problem that comes from that is that when you create your model checkpoints, they're basically coupled with your hardware that you created them on. So in other words, you cannot resume training unless you have exactly the same number of GPUs. And that's just because the distributed checkpoint is tightly coupled with your hardware configuration. And so this creates a lot of inflexibility challenges with resource capacity management. And so the solution here is that we decouple those 2 things. So your checkpoint and your hardware parallelism, or even your parallelism strategies like tensor parallel or pipeline parallel, we decouple those 2 things. And that brings some practical benefits. One is for fault tolerance, right? So if you have a failure, you can continue training with the healthy nodes. You don't have to kind of wait until you get a replacement node. You can continue training. And so that's really great. And the other is faster training. So basically, if you have elastic resources become available, you can take advantage of them to speed up your training just opportunistically until you have to sort of give them up. And this work will actually appear at ATC later on this year. And so the overview here, I'm just going to touch on them very high level. We'll have to chat later on. So the first thing is we recognize that the different parallelism strategies exist, and we provide a way for you to reconfigure that. So you started out with some kind of TP, PP, whatever. We provide a mechanism that allows you to reshape your parallelism strategy. So you can go from any source strategy to any target strategy. And this reconfiguration is pattern-based, which means that it makes it portable. So we provide a language where you can express your parallelism strategy, and so you can rewrite, with that you can rewrite what you want your target strategy to be. So it makes it easy to adapt and apply to other, in various scenarios. And then we've also provided optimizations for this reconfiguration. So here I just highlight some high-level results. One is the reshaping, and this is just to show that, when you do reshape your strategy, your training is not affected. Your convergence kind of remains the same. And so the plot up on the left-hand side is showing that you started out training with one particular strategy, and now you want to reshape to multiple different strategies, and that's kind of just showing that the loss curve is the same. The next plot to it is kind of showing the inverse, where you started out with different strategies, and we're showing that you can go into a new strategy without suffering in your convergence. And then the lower plots are just basically showing end-to-end results in actual training, both for dense and sparse. I'll draw your attention to the middle one, the GPT-176B. This is the big science model training that happened a few years ago. And we actually used this because at that time, the project was going to lose half of its GPUs somewhere midway through the training. And that's when we actually built this technology to enable it to continue training on half of the GPUs that it started with. Yeah, and so, technique has been adopted in many different places, like the big science, like I mentioned, was sort of like, the first one. And so, yeah. Now I'll move on to the next work, which is more of a communication domino, so communication-free training. So a lot of the parallelism strategies like tensor and pipeline parallel, they do, they partition, but then you pay the price of some communication. And so here, the goal of this project is to see how can we reduce that communication cost, hopefully to like 0. And we started out by looking at tensor parallelism. So the plot up there, the top left is showing when you do tensor parallel training of a GPT-13B size model, and it's sort of breaking down the time between computation and communication. And as you can expect, as you go across nodes, your communication time starts to dominate up to like 40% of your end-to-end time. And so the solution here is we introduce some fine-grained overlapping of your compute and your communication. And we can do that either within your transformer layers or across transformer layers. And the plot over there, showing up there, is showing like a Megatron LM, sort of how, if you do tensor parallelism, your transformer computation gets split into computation, which is sort of, you can think of it as the upper side, and then communication at the lower side. If you use domino, you can see down there, we are now sort of doing some fine-grained overlapping, so you don't have those gaps where your GPU is idle or your communication is idle, and that helps you improve performance. So high-level results here, we're showing here that on both for the forward pass and backward pass is just the profiler shots showing that we actually on H200, we're able to completely hide the communication in tensor parallelism completely on a single node. And then we have results comparing against Megatron LM, both in single node and multi-node, and we get, at best about a 16% speed up compared to like Megatron LM. Okay, and then ongoing work, we are integrating with Hugging Face Nanotron. We have some good results there. We're achieving 75% communication hiding at this point. The goal is to get to like 100% communication hiding. We're extending this work to MOE and inference and long sequence training and some quantizations for the communication as well. The next work is deep compile. And so the goal here really is that distributed training optimization is hard. It requires developer work, but in particular, tuning them to get peak performance for different models and different hardware is really difficult, right? And so the idea here is we want to automate this by using a compiler technology, right? And so last year, PyTorch released the Touch to Compile, awesome technology that allows you to basically rewrite your computational graph in a flexible way. And so we kind of leverage that. And so the two key ideas there is that we'll be doing optimization using compiler transformations. Right? And so the first part is we will automatically apply the distributed techniques, whether it's TP, PP, whatever. We will use the compiler to actually do that to the graph. And then we will do something which is kind of classic compiler tricks of profile-guided optimizations. We'll allow the training to run for a while. We'll profile it in its runtime environment, and then we'll tune the parallelism techniques to get the peak performance out from that scenario. Now, like I said, it's built on Touch Compile. The plot over there is just kind of a high-level view. We take a model, we run it through Touch Compile, we get the graph. From the graph, we apply the transformations for optimization and parallelism. We run for a while, we profile while we're running, we figure out what are the optimal settings for the various parallelism techniques, and then we recompile, and we do this over and over again. Since training takes a really long time, within a few hundred iterations, we'll be able to get this done, and then the rest of your time can be spent running at peak performance. We've implemented 3 different optimizations at this point, and we're working on more in collaboration with the community. And I'll show some, let me sort of drill into the 031 to sort of give you a bit more flavor here. So there are 2 aspects to it, like I said, is So here on the left-hand side, assuming you have like a single GPU implementation of your model with a parameter and some operators, 0.3 basically involves sharding the parameters. And so here we can see with the compiler, we're able to automatically apply the sharding instead of having the users have to write it. And then the profile guided part, when you shard parameters, you pay the price of communication, that's the price. But then prefetching is sort of like the standard trick to sort of hide that. But then the problem is how much should you prefetch, when should you prefetch? The profile guide is showing there is showing the memory profile of your training. So you see that at the beginning of the forward pass, for example, you do have a lot of memory. So you can be very aggressive with prefetching, but not so much in the backward pass. And so, but with the profile guided optimization, we're able to detect these patterns and then recompile the model to sort of take advantage of that. So in terms of results, yeah, we're seeing great results, speed ups for 0.3 here, both on the dense model and on the sparse, the mixture model. We're seeing up to like 50% speed up. Another optimization we did was 0.3 with offloading. So basically, here we're able to also just compare it to like baseline 0 or 0 using just pure touch compile. We're seeing over 5x speed up. For the 0.3 offloading. For 0 stage 1, which is just optimizer sharding, we're seeing like over 30% speed up as well. And I'll jump to this is the last project, Deep NVMe. The motivation here is that we recognize that I/O is becoming a key bottleneck as we continue deep learning scaling. And it shows up in a few ways. One, in a few ways because where persistent storage is becoming important. So your data sets, data loading, data preprocessing all involve interaction with just persistent storage. Model checkpointing is sort of a natural one too. You save your checkpoints in persistent storage, and then sensor offloading is kind of becoming sort of important. And so the key idea here is that we note that there are a lot of innovations in the storage space, and we want to build optimizations on top of that. So things like local NVMe SSDs, asynchronous I/O stack that Linux now provides, and then things like NVIDIA GPU Direct Storage that allows direct communication between storage and HBM. And so there we built different kinds of optimizations there. And so the results on there is just showing that on the PCI Gen 5, like sort of the latest, greatest Azure VMs, we can hit almost 50 gigabyte per second disk reads there, about 25 gigabytes writes, and importantly, I'm showing there that as we scale the number of NVMEs, your performance is scaling linearly, so it's kind of cheap to scale. Here are some just application highlights, and I'll just wrap up. So here, the one on the left is just basically showing NVMe offloading, which allows you to inference a very large model on a single GPU that you wouldn't have been able to do because it's not big enough. And so we integrated this into SGLang, and so we can, you can at least use this for like throughput-based offline inference. And over there, we're showing about a 20x faster model checkpointing compared to PyTorch same. DeepSpeed is a community project. It's been that from the get-go. We have over 400 contributors, a number of organizations supporting us, and breaking news today, it's now part of the PyTorch Foundation, which is super exciting. So just invite you to join us, and let's make state-of-the-art AI available to everyone. Thank you.